Okay, this is Chemistry Chapter 9, Lecture number 3. You'll be happy to know I think that this is the shortest of the Chapter 9 lectures. You will need your notes. We're going to start on the bottom of page 6 and we'll finish it out. And it's always helpful to have a periodic table handy. If you've labeled one with the S and P block labeled by the columns, that's always helpful as well. And in the book, the first one that we will work is on page 306. So going over the bottom of page 6 on your notes, rules to determine if a molecule is polar covalent. So first of all, the molecule must have polar bonds, and the polar bonds cannot be of equal strength and pull in opposite directions. All right, so turn your notes over to page 7, and we'll work on your own 9.10, and we're going to fill up this entire page with molecular structures. So 9.10 says, classify the following molecules as polar covalent or purely covalent. All right, A is Br2. So bromine is in column 7. So it has one open slot, 7 valence electrons. It can only take a single bond. Let's draw the other valence electrons. So since it's the same atom, they will have an equal tug. Okay, they have the same electronegativity. So they cancel. If you look back on the last page, the polar bonds are of equal strength. So they cancel each other out. So this would be purely covalent. All right, the electrical, we'll call it a tug, cancels because it's the same atom. It's a tie. The tug of war is a tie. All right, B, CO2. Now we've drawn this one a lot. Carbon, 4 valence electrons. It'll be in the center. Oxygen has 6, okay? 6 valence electrons. So it is a double bond. All right, if you're unsure about that, go back and look at previous lectures where we've drawn this multiple times. And in your notes. So oxygen is more electronegative than carbon. It's to the right of carbon on the periodic table. So it will have polar bonds. However, because oxygen, it's the same oxygen on each end of the molecule, it would be purely covalent. Because just like before, the electrical tug cancels, all right? Oxygen on each end cancel each other out. So once again, that electronegativity tug of war ends in a tie, so that makes it purely covalent. Now, why are we figuring out whether it's purely covalent or polar covalent? You will see when we do 9.11. All right, C is H2S. Now, I believe we've already drawn H2S. We have hydrogen with 1 valence electron, sulfur with 6. Right? If you remember, sulfur 1, 2, 3, let's see, yeah, 1, 2, 3, 4, 5, 6. Each hydrogen has 1. So each of these two hydrogens could form a bond with each unpaired electron. And when you have a single central atom with two single bonds, it forms a bench shape. So the shape does matter. That helps us determine if it's polar or purely. Okay, sulfur is more electronegative than hydrogen. So this is going to have a net pull upwards. So if the molecule will move, okay, it's polar covalent. Okay, and I'll give you a hint here. Bench shape is always polar. All right, always polar. That's not true for all the shapes, but the bench shape will always be polar. All right, pause the video if you're still drawing and writing, and we'll move on to D. All right, D, we have CF2, Cl2. Okay, so carbon, we have 4 valence electrons. Fluorine in column 7, all right, has 7. 2 of those. Chlorine also in column 7. 1 open slot. So fluorine and chlorine can only take a single bond. There's 2 of them. All right, so 2 each. So if you have, let me put this one back together. If you have a central atom surrounded by 4 single bonds, because we have 2 fluorines, 2 chlorines, you have a tetrahedron shape. All right, so we'd have a carbon in the center. Doesn't really matter where you put these, but I'll put the fluorines together, the chlorines together. All right, put the dots around them. Sorry, but I've kind of squished everything in here a little bit too much. Fluorine always wins the electronegativity battle. And then chlorine is to the right of carbon, so it's going to also win. So it definitely has polar bonds. That's one of our rules. But see how fluorine's got different electronegativity than chlorine. So this will have a net pull to the, it'll pull this way. Pulls this direction, all right? It kind of wobbles over to the right. If it moves, if it's going to move, there's no canceling out. Then it's a polar bond. Or polar covalent, excuse me. It's polar. It can be purely covalent with polar bonds if they cancel out, but in this case it doesn't cancel out. Fluorine has different electronegativity than chlorine. So it is polar covalent. All right, I'll go ahead and erase this. Let's look at E. So E is SiF4. So we just drew fluorine. Fluorine column 7 only can take a single bond. Silicon's just like carbon in column 4. So you tell me, just looking at this before I draw it, what shape will SiF4 have? I'll give you just a second. All right, if you guessed tetrahedron, you guessed right. Okay, so you'd have silicon and 4 fluorines. You don't really have to draw all these electrons and everything to answer the question, is it purely or polar covalent? But I want you to get in the habit of doing this, because you are going to have to do that on the test. You'll have several questions where you have to draw the molecular shape. Fluorine always wins the electronegativity battle. It's in the top right corner. So all these fluorines, everything has the same electronegativity around silicon, all the same. So all the fluorine poles cancel out. It's all the same. It's got a big tug-of-war tie here. So that makes it purely covalent. All right, in F we have pH3. I think we drew this yesterday. I think it's in your notes. So look at pH3, and while I am getting the model, you tell me what shape you think it is. All right, did you guess that shape? All right, each hydrogen can only take a single bond. We have a phosphorus in the middle. All right, so 3 single bonds around a central atom gives us a pyramidal shape. Do you remember the bond angle? All right, pyramidal shape, bond angle 107. All right, so phosphorus more electronegative than hydrogen, so this is going to have a net upward pull. All right, so that is going to make it polar covalent. If it moves, it's polar. I'm going to give you a hint. This might help you on the test. The pyramidal shape is always polar. Just the shape forces it to be that way. It's always going to move. So of our shapes, linear can be either polar or purely. You don't know. It depends on the situation. Also, a linear like this can be polar or purely. In this case, it's usually going to end up being purely, but it can be polar. Pyramidal, always polar. Tetrahedron can be either or. Just depends, right? If it has different atoms on those single bonds. And then the bent shape I already talked about, always. So the two that are always, no exceptions, are going to be purely, are always going to be polar covalent, are the bent and the pyramidal. And the trigonal also would always be polar, okay, because you'll have to have a different type of atom here with the double bond than the two singles. All right, I'm going to erase this, and we will finish up this chapter in just a second. Okay, turn over to the last page of your notes. So this chapter had a lot of real estate on the notes, but if you understand it, the homework goes by really quick. Like dissolves like. So polar covalent compounds can dissolve other polar covalent compounds. Purely covalent compounds can only dissolve other purely covalent compounds. So you need to highlight this, okay? Polar dissolves polar. Purely dissolves purely. Okay, and then I've got a little paragraph here about how soap works, because soap molecules consist of long chains that are polar covalent on one end and purely covalent on the other end. The polar covalent end can dissolve, the purely covalent end dissolves purely covalent stains. Polar covalent water molecules then tug at the polar end. All right, so let's draw this out underneath that paragraph. Let's just draw a long soap molecule. Soap molecules are really long, so we'll just draw it like that. All right, and let's say that this is the polar end, and this is the purely covalent end. So this side dissolves oil and grease because oil and grease are purely covalent. So the purely covalent end of the soap molecule will dissolve that. And then the polar end is attracted to water. Well, that's not good spelling. All right, because water is polar, it's that bent shape. So the polar end of the molecule has an electrical attraction to the water. So this end dissolves oil and grease, and then this end pulls it away as you rinse with water. So that's pretty cool. That is how soap, pretty cool. That's how soap works. So let's look at 9.11 and finish this up. So 9.11 is on page, last page, page 308 of the chapter. And it uses the exact same compounds that were used in 9.10. So Br2. Well, we drew that already. It was linear. So if you'll go back to 9.10 and look at that, since we drew it, it's linear. And it was purely covalent. So will it dissolve in water? Right, the answer is no. So you kind of have to go back and look at your 9.10. CO2, that was the linear shape that canceled out, so it was purely covalent. So it's no, it won't dissolve in water. H2S, that was the bent shape that we drew. It's polar. Will it dissolve in water? Yes. It has to be polar to dissolve in water. CF2Cl2. We drew that, and the charges, the atoms did not cancel each other out. Those electronegativities were different. It was a tetrahedron shape, and it was polar. All right, so it will dissolve in water. SiF4. All right, that one was a tetrahedron, but all the fluorines canceled each other out, so it was purely covalent. So that one is a no, it won't dissolve in water. And then pH3, that pyramidal shape, always going to be polar. You can see it if you draw it out, just like we did. So yes, it will dissolve in water. I find on the test that some students miss these. I don't think it's a hard question at all. You just have to know if it's polar or purely. Polar, yes, will dissolve in water. Purely, no. So just be careful on that. All right, the homework is just to finish up the review questions and practice problems. So review questions on page 317. All you have to do is 9 and 10, so that's nice. And the practice problems on page 318, also just 9 and 10. All right, so that'll go really quickly on Friday. If you're watching this in 2020, on Friday, you need to watch the Chapter 9 solutions video. That will be posted. It's really important that you watch this to make sure you correct your papers, because this material will be on a test that you take the week after Thanksgiving, towards the end of the week. Okay, so make sure to watch that solutions video. I will do one video for the review questions and one video for the practice problems. And so that's it. This homework won't take you too long. This is the last new material that I will teach you before January. So you have made it through the first semester's chemistry material. And I don't know when I'll talk to you next. Probably after Thanksgiving if you're watching in 2020.